Hello there, my name is Mark Tschopp and welcome to Empowering the Force, a YouTube channel where I put together a number of short videos on the concepts, the math, the algorithms behind machine learning and neural networks. In today's set of videos that I'm going to be taping, I'm going to talk about different aspects of neural networks. So without further ado, let's go ahead and dive into the course. Okay, I'm going to switch over on my screen. So again, this is part of this Machine Learning for Everyone series that I've done every year on like May the 4th. May the course be with you. Today we're going to talk about neural network basics. Oh yes, I put for everyone, and I really tried to boil it down to be very simple, but the scientist and engineer in me means that I do use some math. I talk about some of the algorithms and try to really break it down to a level where people are more comfortable really understanding what these algorithms are doing. So I mentioned a little bit that in this neural network basics, I'd be covering a number of different concepts and topics, starting with, and I'll go ahead and go to the next slide, starting with neural networks, how they work, what actually goes into making them work, and then talk a little bit about activation functions. A little bit further in this set of videos, I'll talk a little bit about the different parts of training, backpropagation, optimization, initialization and regularization, and then kind of round out the session with multi-class classification models. So what happens when you have multiple things that you're predicting, hyperparameters and how you tune those, and even some examples in Python script. So without further ado, Okay, that's just me being silly. But I was pretty happy that I got the scrolling screen to work in PowerPoint. Oh, boy, here's some more memes, huh? Data Vader? Really? I do not approve. And then I can't go too much without some little Star Trek references. So, here you go. Data fit in perfectly on this slide of a few memes. Here's kind of the outline of the entire course as I kind of put it together. I did talk about machine learning basics already, so there's some videos here that start to explain linear regression and logistic regression. And now in this set of videos, I'm going to talk a little bit about neural network basics. So really the machine learning basics, and by that I mean the linear regression and logistic regression, kind of set us up in a good place to really now layer the complexity a little bit and understand exactly how neural networks work. And this whole course really started with me learning a lot about machine learning and starting with, well, what are some important concepts that people should know about? And I really thought I was going to go with 5 or 10. I actually just sat down and start jotting out and writing down a number of concepts. I've already went through a number of them already in prior videos. And now we're going to get to this other side, which is really all of these different concepts related to neural networks, deep learning, and even these more advanced neural network architectures. So let's talk a little bit about machine learning models. Various mathematical models and algorithms have been around for a long time. In fact, you can even trace back neural networks to when they talked about perceptrons 50, 60, 70 years ago. But one thing I want you to look at conceptually from this graph, go ahead and Control L for laser pointer, is there's really a whole hierarchy of models. We talked about linear regression, logistic regression, and there's a number of other models that I list in the upper left-hand corner of this slide. And then there's your deep learning and neural network models, artificial neural networks, deep learning or deep neural networks, and a number of different neural network variants. And really what the difference is, as you go into these sort of deep architectures where the model parameters really scale up to very large numbers, it provides you with a lot of flexibility. So linear regression, logistic regression, they can capture a lot of simple relationships, but with neural networks, they can learn incredibly complex patterns. So the flexibility of these models is very high. Now the trade-off is that certainly over on this axis, you can understand what the model parameters are doing in a linear regression model. Even logistic regression is easy to understand what these parameters are doing. Now, as you move into these neural networks, and I'll kind of show you, even at a simple level, how it starts to unpack and get more complex, but it becomes much harder to explain what is actually going on in these hidden layers, in these latent space of these neural networks. So again, now I'll kind of move on to how these models work. Okay, so we've also talked about kind of training data, and how these models learn. And I'll just sort of separate it into kind of a small data regime and a big data regime. And the reason that these neural networks are becoming so popular is really the scale of the data continues to improve. And as the data gets larger, you can see here, these other machine learning algorithms don't have the complexity, the number of parameters needed in order to learn all these complex patterns within the data. Shallow neural networks can learn a little bit more. Maybe I'll just say a medium-sized neural network can learn a little bit more. And as you go deeper and deeper and dive into different architectures that really try to make sense of patterns within the data, the accuracy, the performance of these models continues to increase the more data that you feed them. So within the small data regime, there's a number of different models that can capture the patterns there. But as you move towards bigger and bigger data, you're going to need these deep learning architectures in order to really make sense of all the complexity that lies within that data. And I usually say, as you move up, and just notionally, MATLAB, Python, these other coding languages can capture things from small data to very, very large data. In fact, Python is almost a standard for what people often use to capture, and train these large models. In the small data regime, again, very small, you can handle some of these things with Excel. So while I kind of show how they operate with Excel, that doesn't mean that you would actually use Excel if you're sort of in an industry or application environment. So yeah, one of the questions might be like, why neural networks? Why do we even want to use these deep neural networks? And I just kind of wrote it out in text form here. But really the data can come in as the input X, can be numerical, or it can be categorical. The responses can be a metric or a class, just like how we talked about with linear regression and logistic regression. So neural networks can handle either of those. And how it does it is it uses this nonlinear activation function in the hidden layers and a lot of different nodes, each trying to kind of unpack the patterns within the data to learn the nonlinear relationship between the inputs and the outputs. So the advantage is you gain more flexibility to uncover these complex relationships, and the deeper the neural network, the more complexity that it can learn, and the more data that it can handle, to inform those model parameters and capture these patterns in a way that it can make better predictions. So yes, brace yourselves, math is coming. Okay, so now we're talking about the machine learning basics. If you remember when we talked about linear and nonlinear regression, up here at the first line, this is the linear regression part, right? The mx plus b, again, x are our inputs. M is a slope-like parameter that gets multiplied by the inputs, to modify it. And then you're going to add a constant, so sometimes called an intercept term. So this is the linear regression part. And if you recall logistic regression, we then ran this into a nonlinear function. So in the case of logistic regression, that nonlinear function was the sigmoid function. Here it could be any function, and we'll talk a little bit about what these functions or activation functions are in neural networks. And really the power comes through, okay, this might be the first layer, then you insert it into the second layer, and you see this term repeated. It gets multiplied by a slope, add the bias, run it through a nonlinear function. That layer and the nodes gets fed into the next layer where it's multiplied by the slope. You add another intercept term, you run it through the nonlinear function, and so this repeats over and over again. And that's what gives these neural networks the ability to learn such complex relationships. So let's go back and just start to think again about what we learned about linear and logistic regression. So you can see up here, logistic regression. Again, this is multiple logistic regression because we have multiple inputs. So we have x1, x2, and x3. Theta 1, 2, and 3, these are slope terms that act on each of those inputs. Theta naught is a bias term. And then, this whole equation, again, this is your sigmoid function. So you can recast this as, well, this is the linear part, and let's just call that z. And then you're going to pass z into an activation function or a nonlinear function. And here is the sigmoid function, 1 divided by 1 plus the exponential of negative z. Now what you can do is you can represent this whole equation as a computational graph. And so now you may start to see sort of the similarities with those schematics, with all the nodes of a neural network. What it's actually going on here is you have these input nodes. So there's your x1, x2, x3. Each of those is multiplied by its corresponding slope term. So theta 1, theta 2, and theta 3. That bias is actually a node with a value of 1, and it's being multiplied by theta naught. And all of those are coming together to create z. So I like to actually divide this node in two, is how I conceptually think about it. And on the front half is your linear regression part. And on the back half is where you have the nonlinear part. So now you're running it through this function. And after you do that, now you're going to output a value from that node. And in this case, it's going to be your output y. So I kind of put jokingly down at the bottom, but we've just outlined what a one layer, one perceptron, or one node artificial neural network is. Yeah, and so we talked a little bit about some of these neural or some of these data sets and how you might do predictions with logistic regression. Yeah, it's very similar to what a neural network is. However, as you move over into the neural network domain, the terminology changes. So just to reframe it again, just so you understand what we're talking about when we talk about the terminology of neural networks. First, instead of, theta 1, theta 2, theta 3, they often use W for weights. So they call them weights, and these weights can be weight 1, weight 2, weight 3 in this sort of example. Instead of theta naught, they use a B for bias. So now you've changed it from mx plus b or theta times x plus theta naught to a w times x plus b. Z is often used as this intermediate state. So again, referring to up above, that's the linear regression part. F of z, g of z, is just describing this nonlinear function and how it's going to take the linear part and that's going to be an input into the nonlinear function. So that's called the activation function. A for activation is often used to describe the output of that. Any of the middle nodes, so when you see like multiple different layers of a neural network, the middle node is often termed a hidden layer. And then forward propagation is you insert x's on one side of the neural network and you predict y's. Backward propagation is when you go from y's in the reverse direction back to x's. So, again, just when you're hearing about neural networks, you'll often hear a lot of these terms: weights, bias, activation function, hidden layers, forward and backward propagation. So we'll talk a little bit more about some of these. Yeah, and I just told you like how uninterpretable. I think the math here, a lot of people can kind of follow along with. So it sounds like, maybe this isn't as hard to understand or explain as I thought about. Really, the problem comes from when you have so many different layers and so many different nodes. That's really where the hard part of really understanding what all these individual nodes are doing within these neural networks. And yes, this kind of builds on really knowing about logistic regression. Yeah, and to be honest, I forget if I made up these these memes or found them on the internet. But yes, the moment you start to realize that really logistic regression is also a very simple neural network, maybe at its most simple. Okay, so I think this is actually a video. Maybe to set it up, I'll turn my laser pointer back on. So what you can see up here is the weights and the bias. So I've named them, B1. So the bias for layer 1, the weight for layer 1, and then underscore, and I give it a number 1 through 10. Each of those numbers 1 through 10 is where these weights are acting upon our inputs, which are numbered x1 through x10. So I've already went and optimized this model so you can see kind of the optimized model weights, and then we're going to go through and do logistic regression. So this is just a reminder of how logistic regression works, but I want you to kind of look at it in terms of, okay, really this is a very simple neural network. Okay, you can see again up above here, I like to go up and actually name the variables. So bias 1 underscore weight 1 underscore. I take all of the inputs and can call them x underscore. I can go over compute z. Remember, it's a matrix multiplication, so mmult in Excel of x comma w. So x underscore weights in the first layer underscore, and then you're going to add in the bias. So plus bias 1 underscore. Okay, so there's our z's. If you remember for logistic regression, again, before we go to that function, you can call it z1 underscore. So now we're going to make a prediction coming out of that node. So 1 divided by 1 plus the exponential of negative z, z1 underscore. And there you go. There's our prediction. You can kind of see, again, because the sigmoid function maps those linear results into a space between 0 and 1, which is a good space to be in because our actual y values are binary, so 0 or 1. The loss function would be negative y times the log of y hat minus 1 minus y times the log of 1 minus y hat. So again, that's your binary cross-entropy loss function. The cost function is simply the average of that loss function. So if I select all of that, the average is a cost function. If you wanted to, again, for regularization, you do the sum of squares of the weights. Sum of squares of weight 1 underscore. You can multiply it by a lambda value and obtain a new cost function. So it's the cost function of the losses plus this penalty term that really penalizes the weights from becoming too large. And then you can take either of these cost functions and use Excel's solver or some sort of optimization function in order to drive the cost to a minimum while changing the model parameters. Again, your weights and your bias. Okay. So we just talked about this neural network building block that's up here in the upper left-hand corner. Now let's just add just a little bit more complexity, right? So we had 3 of these inputs when we explained that up above. You can also call these activations in the 0th layer. So you'll see sometimes that people talk about them as activations coming from nodes in the 0th layer. So we have A naught, which is the bias term, and then A1 through A3. You can see here we've added a hidden layer. So this would be termed a hidden layer, and we have 3 nodes in that. There's this extra node for the bias. Again, it's not connected to anything behind it, so I just put it within this layer. In actuality, there's 3 nodes here, and then those are going to be combined for this last building block for this output node. Okay, so step 1, you have your x's and your y's. You have your activations coming out of the 0th layer. So now you're going to calculate Z1. So Z in the first layer is the weights in the first layer times the activations from the 0th layer plus the bias first layer, which is really this activation from the 0th layer. But there's going to be 9 weights, 3 biases. So actually each one of these lines connecting it from the 0th layer to the first layer is going to be a model parameter. So now you have your weights and your bias. Step 2 would be, okay, you need to calculate the back half of this node. So you've calculated the linear part, which is Z. Now you calculate your activation, so the value coming out of these nodes. So the activation in the first layer is going to be an activation function in the first layer times Z from the first layer. So there we go. That's very similar to what we talked about with logistic regression. Now you're going to calculate z in the next layer. And you can kind of see here the commonality with step 1. So step 3, z in the second layer, is equal to weight in second layer times activation from the first layer plus bias in the second layer. And now you pass it through another nonlinear activation function. So F2 is an activation function in this second layer node. So that could be your sigmoid function, for instance. You're going to multiply z from the second layer, run that through this activation function to produce an activation function from the second layer, which is actually your prediction, y hat. So there, that's a very simple example. I'm just going to go ahead and run this through very quickly. So here we actually started with some values. So the first thing you can do is go ahead and normalize these values. So subtract the average, divide by the standard deviation. In some of my examples, I've already done this, to sort of scale these values. Here we had to do that starting off. You can see up above the weights in the first layer, the bias in the first layer. So this is going to be matrix multiplication of z, comma, weight 1 underscore. So that's going to be three columns for the 3 nodes in that first layer, plus the bias. Okay, so you see how with these dynamic arrays, it automatically filled in all of these. This tan h is a hyperbolic tangent function. So that's another very common activation function in neural networks, and you can see how easy it was to implement in Excel. Now you have your output node. Again, it's a matrix multiplication of A1. So you can see the activations from the first layer times the weights of the second layer, and then add in the bias for the second layer. That's your z, and then that actually gets combined with 1 divided by 1 plus the exponential of negative z. So there we go right there. That gives you a prediction. You can see the loss function there, the accuracy on this very simple model. So these are all things that we've talked about kind of at length when it comes to things like logistic regression, for instance. Okay, so now we've done one hidden layer. What about deep learning? Well, if you kind of look here, let's extend this to 5 layers. So 4 hidden layers and then an output node. And I show that down below. Let's see if our laser pointer's still on. So we have 1 layer, 2 layer, 3 layer, 4 layer. And here I've just kind of used a notation to show that, okay, z for any of these layers, let's say the third layer, z for the third layer is equal to the weights for the third layer times the activations from the second layer plus the bias from the third layer. And then the third layer activations are running z for the third layer through some nonlinear activation function. And this is what gets carried back up to the step 1 in the next layer. So this is how forward propagation works. You can see kind of the neural network that I've composed here. If you were to count all these lines, you would see that there's about 39 weights, 5 biases. In fact, I'm not sure if I rechecked that, but hopefully that's correct. And so that kind of describes, how these deep neural networks look and how they work. Now, why is it able to understand all of these complex patterns? Well, let's write out this function. I mean, if you look at the prediction, what is it actually doing? Well, it's taking your inputs, multiplying by a weight, adding a bias, running it through a nonlinear function, multiplying that by a weight, adding a bias, running it through a nonlinear function, and it's continuing to do this repetitive, sort of linear and nonlinear part. And that's really what gives it all of this flexibility to represent very complex patterns and relationships. Also, in some cases, to memorize. When I talked a little bit about overfitting, neural networks are really good at overfitting. And we'll talk a little later about how we regularize neural networks to make sure that they're not just memorizing what you're giving them in the training data, that they're also learning how to generalize when given new data. And if you actually look at this from a linear algebra point of view, what it's actually doing is we've got this, this matrix of weights. It's being multiplied by our activations or our inputs. You're adding a vector of biases, and you're running them through some nonlinear activation function. So just to kind of highlight, if we look up here at this kind of highlighted node, it's very faint. Activation 1 in this respect is taking all of these weights, multiplying it by the inputs, adding a bias. Activation 2 is taking this middle set of weights, multiplying it by this, adding a bias. And again, activation 3 is doing the same thing. In reality, these weight matrices, are extremely large. So when you think about things like these large language models, these weight matrices can be thousands or tens of thousands, in each dimension, in order to capture these complex relationships. Now, I had just a few slides on activation functions. One of the things that activation functions do, when we talked about the sigmoid activation function from logistic regression, it was really great for taking values that could be negative infinity to positive infinity coming out of our linear component, and mapping it to a space in between 0 and 1. So this is really nice. Hyperbolic tangent does a similar thing in between -1 and 1. But these activation functions, the other part of it is this derivative. So we talked about gradient descent already, and gradient descent requires a derivative in order to work. So in a similar way, we're going to train these neural networks, and we're going to need the derivative. And one of the things that has evolved is that you choose the activation function such that you can store this value. So this f of z, this value as it's going forward and forward propagation. And then when you need the derivative to actually optimize the parameters, you store this value and you just insert it into an equation to get the derivative. And this makes it much more efficient in terms of how it trains these models. So they've chosen very simple activation functions, but also activation functions that have very simple derivatives. Oh, and for those of you that have taken my course, or I may put my true-false test online just for people to try out, I had true-false statements. So here's a true-false statement. 4 common types of activation functions are tanh, ReLU, squeaky ReLU, and sigmoid functions. This is actually false. One of those is not correct. So we've talked at length about how these neural networks now are a combination of sort of this linear model, and then we're going to add in this nonlinear model. And we're going to encapsulate that within each node within the neural network. Rectified linear unit is actually one of the more popular activation functions. And I usually do an example when it's live of, hey, give me a number. 0, I said I'll return 0. 4, I return 4. 8, 8. 132, 132. Okay. Then I'd say, well, you can give me negative values. Okay, -4, 0. -8, 0. -746, I say 0. So, you kind of understand when it's less than 0 or negative value, you return 0. When it's a positive value, you return the same thing. So it's almost crazy how simple this activation function is, but it is nonlinear. So here's 4 very common activation functions. Again, the sigmoid function is the upper left. This is the one that we've already talked about. Hyperbolic tangent goes between -1 and 1. So this is also very popular for using as an activation function. And you can see the equation that I wrote up here as well as the derivative. So again, you see here the equation, and if you store this value, then you can actually plug it into this equation to obtain the derivative when you need that for optimization purposes. ReLU is just the maximum of 0 and z. So obviously 0 is greater than anything negative, and anything positive is going to return itself. And the derivative is going to be 0 in this domain and 1 for anything positive. And then there's also other variants off of this. One's called leaky ReLU, probably the simplest extension, which is you just take this alpha parameter and give it a slight slope in the negative region. So you're going to modify it by some value, could be like 0.1 for instance, and this is going to return at least some value when it's negative. And so that's going to enable you to actually feed at least some value from the derivative into these optimization routines, which might nominally help the model parameters. I kind of list down below that ReLU is this rectified linear unit. That's what it stands for. And there are all sorts of different attempts at capturing different relationships based on this. In fact, GALU is actually commonly used in a lot of these large language models. And yes, for those of you that didn't catch it the first time, I put squeaky ReLU in this pretest true-false statement. So some people got fooled. It's actually, if you look it up in cognitive psychology, there's a serial position effect. You tend to pay more attention to the first and the last. So tan H, the sigmoid function, and pay less attention to interior parts of a list. So I kind of tried to fool people by placing it in one of those spots that people tend to not pay that much attention to. I also have an Excel sheet, and I'm going to go ahead and upload this. Within the description, I'll include a link, and if people want to go and try out these different activation functions, they can enter a value for alpha, for x, and see what these models return. Oh, I guess there's a video. So there you go. Yeah, I'm not sure we need to let that play out. Okay, so with that, we've kind of described some of the ways that these neural networks work. I'm going to go ahead and switch over. And we are going to go ahead and go back. Okay, thanks. In the next video, we're going to talk about how we train these different neural networks. So again, I'm going to post some other videos of really how backpropagation works, and how the optimization schemes work for neural networks. Okay, thank you, everyone.